Welcome to week 2 of cellular mechanisms of brain function. Last week we learned about the phospholipid bilayer that forms the cell membrane and electrically acts as a capacitor. We also learned about ion channel proteins that span the plasma membrane and form conductors with specific reversal potentials given by the ionic species for which that ion channel is permeable to. These reversal potentials were given by the Nernst equation, calculating from the concentration gradients distributed across the plasma membrane. We also learned that membrane potential was signaled in a complicated way across the extended neuronal arborizations of real neurons. Changes in membrane potential in one part of a neuron were signaled to other parts of a neuron, but only after spatial and temporal filtering. Temporal filtering occurred approximately on the 10 millisecond timescale given by the membrane time constant. The length constant of the cell, on the order of several hundreds of microns, defines the length scale over which steady-state voltage differences are propagated across neuronal arborizations. Now, in real neurons and in the real mammalian brain, signals need to traverse much longer distances. One part of the brain needs to be able to communicate with another part of the brain, spanning some 20 centimeters, and some parts of the brain need to be able to communicate down the spinal cord, extending meters. Given that we know that membrane potential is filtered significantly by the cable properties of neurons, how then do reliable signals arise in the nervous system? The answer comes in the form of the action potential, a digital, all-or-none signal that's actively propagated across the neuronal arborizations through voltage-gated ion channels. Today, we'll study the biophysics of these voltage-gated ion channels. Last week, we discussed linear channels. These are ion channels where the conductance is independent of the membrane potential, and this then allows us to plot linear current voltage relations, so-called ohmic conductances. Today, we'll think about nonlinear conductances, where the permeation of cations through the ion channel depends upon the membrane potential. This gives rise to nonlinear IV plots where the conductance at one potential might be very far from its linear counterpart. Such nonlinear conductances give the nervous system enormous computational power. How can an ion channel be voltage dependent? Let's return to look at the protein structure of voltage-gated ion channels. The ion channel is made out of a chain of amino acids that span from the inside to the outside of the plasma membrane, meeting the lipid bilayer in parts and in other parts meeting an aqueous intracellular aqueous channel that allows the ions to permeate across the plasma membrane. If we look down upon the face of the plasma membrane and see the phospholipid head groups and the ion channel from the outside, we would see a view something like this. Here are the phospholipid head groups, here are the red subunits of the ion channel. Voltage-gated ion channels are composed of 4 similar subunits. Sometimes they're part of the same protein, sometimes they're part of different proteins that come together. In any case, they form a tight association, these 4 subunits, and down the middle, of course, is the ion conducting pore. Each of these subunits is composed of multiple transmembrane segments. Here you see an example ion channel with the typical 6 transmembrane alpha helices. We have alpha helix 1, 2, 3, 4, 5, and 6. There's a color coding of these transmembrane alpha helices, and you'll see that there's a yellow part here composed of S5 to S6, and that turns out to form the pore lining region of the ion channel. So next to these alpha helices, we have the aqueous pore, and in fact, this turns out to be where the selectivity filter is located. The red alpha helices, S1 to S3, are here on the outside of the protein. They need to interact with the phospholipid bilayers, the lipophilic part of the ion channel. And here, colored in blue, is a special part of the ion channel for voltage gating, the so-called S4 voltage sensing region. The S4 voltage sensing domain that you see again here in blue is interesting and forms a sort of unit that can move and is relatively mobile within the structure of the ion channel. The S4 voltage sensing region is, interestingly, positively charged. It's full of arginine amino acids that have positive charge on them. The ability of the S4 region to be relatively mobile and that it's charged allows it to interact with the electric field across the plasma membrane. At hyperpolarized potentials, there's a strong electric field that is from the outside to the inside. That electric field acts upon the charges of the S4 voltage sensing domain and pushes it downward towards the inside of the cell. The S4 voltage sensing domain is attached to a gating mechanism, the voltage gate. When these positive ions are pushed in towards the inside of a cell, the gate swings up and it's closed. The ion channel cannot open and cannot permeate ions. If, on the other hand, we switch to a positive membrane potential, the positive charges on the S4 voltage sensing region are moved out in the electric field. They act upon the voltage gate of the ion channel, open it, and allow for ions to flux when the ion channel opens and closes in its random stochastic manner. So the movement of the S4 voltage sensing domain gates the open probability of a voltage-gated channel in a membrane potential fashion. We know that there's a physical reality to the movement of these charges on the S4 voltage domain because even in the absence of any ion flux through the ion channel, you can measure a gating charge if you change the membrane potential rapidly to a positive value. You can see that there's a capacitative current, very brief, very fast on the microsecond timescale that indicates the capacitative movement of these positive charges on the S4 voltage sensing domain as it moves out. So, at the level of an individual ion channel, where we'll now consider the difference between a linear and a voltage-gated ion channel on the right, for a linear ion channel, the open probability of that ion channel doesn't depend upon the electric field that we have. The open probability will be the same if there's a membrane potential of plus 60 millivolts or minus 60 millivolts. And here we imagine, for example, an ionic conductance that has a reversal potential at 0 millivolts. This would be the current, the voltage, and we have a linear conductance. And so at a membrane potential of plus 60 millivolts, we have a certain amount of time that the ion channel spends in the open state compared to the closed state. In this case, maybe it's in the open state about half of the time. If you go to negative hyperpolarized potentials, the open probability of a standard linear ohmic ion channel doesn't change. The open probability is still about 50%. But now, of course, when the ion channel opens, then the currents flow in, because we're in this symmetric situation here where we have plus 60 and minus 60 millivolts. The amount of current here is the same at both ends in an ohmic ion channel with reversal at 0 millivolts. For the voltage-gated ion channel, the situation is very different. At negative potentials, the ion channel has a low open probability. Remember, the S4 gating area here is positive, and the gate is closed at negative potentials. So this channel spends relatively little time in the open state. When it does open, however, we get the full normal single channel currents, just as we would in the linear situation. What changes through the voltage dependence of voltage-gated ion channels is the open probability. The probability is a function of the membrane potential. At positive potentials, the gating of the S4 voltage gating region is then changed. The S4 region moves out, the gate is then opened, and ions can flux. The open probability then increases at positive membrane potentials for a voltage-gated ion channel. These changes in open probability can then be either summated over time, where we take a mean current flux across the stochastic opening and closings of this ion channel, or we can think of many ion channels on the cell membrane that are opening and closing independently of each other, and we then have a mean conductance. That's of course composed of the single channel conductance times the number of ion channels, and of course together with the open probability of that ion channel. And so for a linear conductance, the conductance is independent of membrane potential, so it's a flat line. The conductance is the same at positive and negative potentials, because the open probability is the same at open and negative potentials. And we've agreed that the single channel conductance is not a function of voltage. For the voltage-gated scenario, we have a change in open probability with voltage. At negative potentials, the open probability is low, and the conductance is therefore also low. As we depolarize, we move the S4 voltage gating region out, the voltage gate opens, and the open probability of the ion channel increases, and we move up here on the conductance until we reach some sort of steady state region here where the ion channel is saturated with respect to its voltage dependence. If we now think specifically about sodium and potassium channels, and voltage-dependent sodium and potassium channels are amongst the most important voltage-gated channels in the nervous system, we now need to think, for the sodium and potassium channels, about their reversal potentials. And we know that sodium has a positive reversal potential somewhere around plus 60 millivolts, and potassium has a negative reversal potential somewhere around minus 90 millivolts. And so the single channel currents, what would be flowing through a single sodium channel at different membrane potentials as the ion channel opens and closes, so this single channel sodium current will then be linear and reversing, of course, at the sodium reversal potential. Similarly, the single channel potassium currents as the ion channel opens and closes will also be linear with respect to voltage, and will of course reverse at the reversal potential for potassium. For voltage-gated sodium and potassium channels, in general, they become activated at relatively similar membrane potentials. And so somewhere around minus 40 millivolts and more positive to that, the ion channels begin to open. The voltage-gated sodium channels increase their conductance above minus 40 millivolts, and the same is true for the voltage-gated potassium currents. And so there's a regime here hyperpolarized to minus 40 millivolts in which there's very little conduction through the voltage-gated sodium and potassium channels. They're closed at most resting membrane potentials. And at more positive potentials to minus 40, they begin to become activated in a strong and steep manner, becoming almost fully activated around 0 millivolts. If we then convolve this voltage gating, the change in the open probability of the voltage-gated sodium channel with respect to voltage, we convolve that open probability with the single channel currents and the reversal potential at the sodium reversal potential, we see that we get a current voltage relationship that looks something like this. At negative potentials, the ion channel is closed, and therefore there's no current that flows. As we move through the minus 40 millivolts and the open probability begins to become significant, we then get single channel conductances that are substantial and give rise to an inward current. As we keep depolarizing, the voltage gating saturates, we hit the reversal potential for sodium, and we enter the linear conduction regime. And so we have this interesting biphasic situation where between the physiological range of membrane potentials from minus 90 to around plus 60 millivolts, we have an inward current that's generated by the voltage-gated sodium channel. For the voltage-gated potassium channels, the situation is very similar. At negative potentials, the conductance is basically closed, and so there's nothing carried by the voltage-gated potassium conductance. As we depolarize beyond minus 40 millivolts, it activates, and we see now that there's an outward current that we can then compute by multiplying the overall open probability of the potassium with respect to voltage and the single channel currents that go through it. As we keep depolarizing, the more and more conductance is activated until we hit this linear regime, and that's what we see here. We end up in this linear regime here. And interestingly, again, in this range of the physiologically relevant membrane potentials from minus 90 to plus 60 millivolts here, we always have an outward current in terms of what can be carried by the potassium channels. So we've seen some interesting features of voltage-gated ion channels. They're largely closed at resting membrane potentials. Membrane potential is normally somewhere in the range from minus 70 to minus 50 millivolts. In this range, the open probability of voltage-gated sodium and potassium channels is very low, and they'll make very little contribution to the overall conductance of the membrane. At more positive potentials to minus 40 millivolts, the open probability increases sharply, and the voltage-gated ion channels then begin to conduct and can contribute to the overall conductance of the cell membrane. The change in conductance of the voltage-gated ion channels is not because of a change in the single channel conductance, but it is a change in the overall open probability. Let's see how voltage-gated ion channels can contribute to changing membrane potential in neurons. Let's consider a cell that has voltage-gated sodium and potassium channels, each of which has a single channel conductance of roughly 20 picosiemens. The input resistance of a cell, its total input resistance, is somewhere around 50 megaohm typically. And that corresponds to an input conductance of something like 20 nanosiemens. So this is the leak conductance of a typical neuron. And it's dominated by a leak potassium conductance that keeps membrane potential somewhere around minus 70 millivolts on average. In order for the voltage-gated sodium or potassium channels to have a major impact upon membrane potential, we need for these conductances to get close, at least in the same ballpark as these leak conductances. Remember that the membrane potential goes something like the sodium conductance divided by the total conductance and the reversal potential for sodium. So if the total conductance is dominated by sodium conductance, the membrane potential will tend towards the reversal potential for sodium. So if we want the voltage-gated sodium channel to make a considerable impact upon the overall membrane potential, the overall sodium conductance must somehow at least get close to the total conductance of the cell. And we said that the leak conductance is somewhere around 20 nanosiemens. And so if we want the voltage-gated sodium conductance to make a considerable impact upon membrane potential, the total voltage-gated sodium conductance also needs to be somewhere around 20 nanosiemens. The single-channel conductance is around 20 picosiemens. This is 10 to the minus 9. This is 10 to the minus 12. There's a factor of 1,000. So something like 1,000 sodium channels are needed in order to make a substantial impact upon the membrane potential of a cell. And indeed, most neurons have high concentrations of voltage-gated sodium and potassium channels, so that exactly this, they can change the membrane potential rapidly in a voltage-dependent manner in order to perform nonlinear computations. Let's see what happens if we open a voltage-gated sodium conductance on a cell. Let's imagine we have a neuron that has some leak conductance and it's largely governed by potassium. In addition, we can then add a voltage-gated sodium conductance. Now, we also have the current voltage relationships for the voltage-gated sodium conductance, and it looks something like this, with the reversal potential for sodium somewhere at around plus 60 millivolts, and the typical cell is sitting somewhere around here at minus 70 millivolts, a time where the current flux through the voltage-gated sodium channel is basically zero. What if we were now to depolarize the cell a little bit? And we'll take it a little bit in this direction. We'll take the membrane potential to minus 50 millivolts. At this stage, there's still very little current that flows through the voltage-gated sodium channels, and they probably wouldn't contribute very much. But as we depolarize just a little bit more, the current flux begins to flow in. There's a considerable influx of sodium into the cell as we open the voltage-gated sodium channel. So we depolarize the membrane potential a little bit. That opens a voltage-gated sodium conductance. That voltage-gated sodium conductance leads to an inward current. That inward current will bring more positive charge inside the cell and will cause the membrane potential to further depolarize. Depolarizing the membrane potential further will lead to an even larger inward current, which in turn will depolarize the membrane potential even more, and so on. We get into a positive spiral where depolarization increases the voltage-gated sodium conductance that further increases the charge influx, further depolarizing the cell. And if we think about membrane potential with respect to time, we depolarize it a little bit, and suddenly the voltage-gated sodium channels begin to participate, and we're in this explosive situation where membrane potential has this positive feedback loop that takes us towards the reversal potential for sodium, somewhere around plus 60 millivolts, depending upon the strength of the leak conductances. So voltage-gated sodium channels give rise to an explosive sodium conductance, where a small bit of depolarization will give rise to a positive feedback loop, taking the membrane potential towards a sodium reversal potential. Let's now consider voltage-gated potassium conductance. The current voltage relation has similar features. We have reversal potential at minus 90 millivolts for the potassium reversal potential. We have the activation of the voltage-gated potassium conductance at around minus 40 millivolts, so it's zero conductance here. This is a current, this is the voltage, and then somewhere around minus 40 it begins to conduct, and we end up with the linear IV relationship here, with potassium always forming an outward current. Potassium will then always want to leave a cell and will then always make things more negative inside the cell. So in contrast to what we saw with the potassium conductance, the sodium conductance rather, where we had the positive explosive feedback, here, as we depolarize the cell, we increase the potassium conductance, but that makes it more negative on the inside and will then be a stabilizing influence. So if we depolarize the membrane potential, that will certainly lead to an increase in the potassium conductance. But an increase in the potassium conductance will, on the other hand, lead to a reduction in the membrane potential. And so we have a stabilizing influence of voltage-gated potassium conductances. For a given membrane potential, if we perturb it by depolarizing it a little bit, the activation of voltage-gated potassium channels will tend to hyperpolarize the membrane potential and take it towards the reversal potential for potassium, around minus 90 millivolts. So in today's lesson, we've learnt a number of interesting features about voltage-gated ion channels. Voltage-gated ion channels have a specific voltage sensing domain, the S4 region, that's highly charged and is very sensitive to the electric field across the plasma membrane. At positive potentials, the gate opens, allowing ion channel permeation and high open probability. At negative potentials, the S4 voltage sensing domain swings in, the gate shuts, and open probability is low. Open probability is therefore the key feature that's regulated by the voltage-dependent gating of ion channels, whereas the single-channel conductance remains unchanged. The voltage gating of the sodium channel, because of its positive reversal potential, leads to an explosive depolarization once you get into that voltage gating activation regime of the sodium channel. On the other hand, voltage activation of the potassium channel acts to stabilize membrane potential, hyperpolarizing the membrane potential towards the potassium reversal potential. It turns out that a dynamic interplay in terms of the kinetics of the opening and closing of sodium and potassium channels underlies the generation of the action potential. And in the next lesson, we're going to look at those voltage gating kinetics of the sodium and potassium channels.